Hi, so the focus has been recently on finding techniques of integration, finding ways that we can take integrals that we didn't know how to do before. So we have two more to do. The one we're going to do today is called Trigonometric Substitutions. And basically, you're going to be looking for this method when you see integrals that involve these three things: the square root of 9 plus x squared, the square root of 4 minus x squared, the square root of x squared minus 25. So a is a constant and x is going to be your variable. So I don't really have to explain too much, I just have to kind of show you the technique. So I'm going to go right into a problem here. And you can see that's the square root of a squared minus x squared. Always what you're going to do is set up a right triangle. And the variable that you're going to have in your new integral is going to be theta. It's sort of akin to a u substitution. This is like a theta substitution. So what we're going to do is make theta one of the angles in this right triangle. And then on our sides, we're going to always put x and a, and then whichever one of these three we're looking at. So in this case, we want 4 minus the square root of 4 minus x squared to be on one of these sides, and 2 and x to be on the others. So we just have to use Pythagorean's theorem and realize in this case, the biggest side is going to be 2. And then I put x over here in the square root of 4 minus x squared on this side. And you can always check it out. You can square this, add them together, and see if you get this. So it is important that you get them on the right sides. So the first thing you're going to do then is create what x is. So in this case, x divided by 2 in this triangle is the sine of theta. So you can say x is 2 sine of theta, and then you're always going to get the differential, dx, because you're going to need it in every integral. So dx is 2 cosine of theta d theta, and then this is going to be in our integral, so we have to find out what it is in terms of theta. So we're going to use this divided by this. So the square root of 4 minus x squared divided by 2 would be the cosine of theta. So this is 2 cosine of theta. And then we just do the substitutions. So dx is 2 cosine of theta d theta. X squared would be 4 sine squared of theta. And then this square root is 2 cosine of theta. And there's no guarantees. We just have to hope that this is better than what we started with. Hopefully, and often this is the case, we get some cancellation. So you can cancel the 2 cosines of theta. You can take the 4 out front here as 1/4, and you're left with d theta over sine squared theta. And at first thought, that isn't so great, but if you remember that 1 over the sine squared theta is the cosecant squared theta. Now normally that's not a great trade, but we know this is one of the formulas that we learned at the very beginning when we did trigonometric integrals. The antiderivative of secant squared is tangent, so cosecant squared is minus the cotangent. And then we have plus c. But just like with u substitutions, we don't want to leave the answer with a theta in it. So what we do is go back and see what is the cotangent of theta in our triangle. the cotangent would be this side divided by this side. So you get the square root of 4 minus x squared divided by x. And we've solved our first trigonometric substitution. So we'll go on to a second one. Again, this one's a little more hidden, but is this one of these? Well, if you have to think of that denominator as being the square root of x squared plus 9 cubed. So it does have a square root of a squared plus x squared, where a is going to be 3 this time. So we again make our right triangle. Theta is one of the acute angles. And then we always have to have x and 3 and the square root in it. Now this time, because there's a plus in between there, that's going to be the biggest side. That's going to be the hypotenuse. So I put x here, 3 here. Now these could go either way. I've always found that it's best to put x across from theta, if possible. If not, put this across from theta. It always would work the other way, but from my experience, it comes out slightly easier if you do it that way. Anyway, the first thing we always do is find x in terms of theta. So x divided by 3 is going to be the tangent of theta. So x is 3 tangent of theta. So dx is 3 secant squared of theta d theta. That's always the first step. Now we have to get the square root. So that divided by 3 is the secant of theta. So this is 3 secant theta. Once you've got all 3 of those, then you do your substitution. Dx is 3 secant squared of theta d theta. Now, this, if you look at it this way, is what we've got right here, cubed. So you get 27, and then you get secant cubed of theta. And always at first when you look at it, it's kind of scary. But if you just take that out front, and then you cancel secant squared of theta with secant squared of theta, you're left with 1/9 the integral of d theta over secant of theta. And again, at first thought, you might be a little afraid of that. But remember, 1 over the secant of theta is the cosine of theta. And that is a really nice thing. The antiderivative of the cosine of theta is the sine of theta. And you add your plus c, and the last step, again, is to go back into your triangle and see what the sine of theta is. The sine of theta is the opposite over the hypotenuse. X over the square root of x squared plus 9 plus c. And that should be your answer. Okay, so I did one that had the number on the hypotenuse, one where we had the square root. So maybe we'll do one where x is the biggest side, because you have x squared minus 25. So x has to be bigger than 5, and it's going to be bigger than this square root. So when I do my triangle this time, I'm going to have x as my hypotenuse. And like I say, I like to avoid having the number across from theta, so I'm going to put 5 down here and the square root of x squared minus 25 on this side. But still the same idea. I go x divided by 5, and that's the secant of theta. And then dx is going to be 5 secant theta, tangent theta, d theta. It's good practice on our derivatives of trigonometric functions. And then the square root of x squared minus 25 divided by 5 is the tangent of theta. And here we go into our hope mode. We put it back in and hope we get something that's going to be better than we started with. So dx is 5 secant theta, tangent theta, d theta. X squared would be 25 secant squared of theta, and the square root is 5 tangent of theta. Looks a little bit scary, but 5 tangent theta, 5 tangent theta. Bring the 1/25th out front, and we've got secant divided by secant squared. And we're left with 1/25th, the integral of 1 over the secant of theta, which is the cosine of theta again. So things are working out very nicely for us. So we get 1/25th, and the antiderivative is the sine of theta plus c. This time the sine of theta is going to be the square root over x. Plus c, or just to make it look a little bit nicer, over 25x plus c. And you've got an answer. So we did one of each kind. So let's just try 2 other problems that are slightly different. So this one we have to decide what is the variable here. It's not x, there's no x there, but you see your differential du up here. You know that u has to be our variable, and then a is going to be the constant. So this time we're going to set up a triangle. The sides are going to be a and u and the square root of a squared plus u squared. Well, because it's plus, that's going to be on our hypotenuse. And I like to put then across from theta the variable, and then I'll put my a on this side. So, well, the first thing I have to do is get what my variable is. So u divided by a is the tangent of theta. So du is a secant squared of theta d theta, and this divided by a, the square root of a squared plus u squared divided by a is the secant of theta. So we get that. Now we go through and rewrite it. Du is a secant squared of theta d theta, and this is going to be this squared. So you get a squared secant squared of theta. And lo and behold, just about everything cancels. Secant squared, secant squared. you're left with just 1 over a outside, and then you have the antiderivative of d theta. The antiderivative of d theta is theta plus c. Now you can't leave it with theta, so you have to go back to here and solve for theta. The tangent of theta is u over a, so theta is going to be the inverse tangent of u over a. So your final answer is, and I'm going to write what the problem was again, it's equal to 1 over a times the inverse tangent of u over a plus c. Now, not only did we solve this problem, but we've got like a formula, something that we did earlier in the year when we were working with inverse trigonometric functions. We came up with that form. It's one of our 10 big forms, except I didn't have the a in there. What if a was equal to 1? Then you'd have the, and let's let, so we'd have du over 1 plus u squared to be the inverse tangent of u plus c. That was one of our big 10 forms. This just makes it more general. So if you were to get a problem like the integral of dx over 9 plus x squared, back when we did those, we had to get rid of that 9 by factoring things out. Now we've got a formula. We could just say that x is equal to u and a is equal to 3. So the answer to this is just going to be 1/3 the inverse tangent of x over 3 plus c. So this is a way that formulas can be derived. Okay, so we haven't done one yet that's been a definite integral. So I came up with a problem here. Well, I didn't come up with it, but it's finding the area inside an ellipse. This has been something that people have wanted to know for a long time. So say we have x squared over a squared plus y squared over b squared equals 1. An ellipse that looks like this, and we want to find the area inside of it. Well, because of the symmetry of it, and because this is going to be a fairly difficult problem, I'm just going to take that one section right there and then multiply by 4. So the first thing we always do is make our little rectangle, but we have to find the height of this rectangle. So that's going to be the y value on this curve. So we have to solve for y. So y squared over b squared equals 1 minus x squared over a squared, or y squared equals b squared minus b squared over a squared times x squared. So what we want to do is get a common denominator. We can say y squared equals a squared b squared minus b squared x squared all over a squared. Or b squared over a squared times, let's see, let me get this right, b squared over a squared times y, when you solve for y, you're going to get plus or minus the square root of this. So it's going to be b over a, the square root of a squared minus x squared. But we're only looking at the positive part up here. So that is going to be the height. So if I take the area, it's going to be 4 times the integral from 0 to a, and then the height is going to be the plus side of this. So it's going to be b over a times the square root of a squared minus x squared. And I can bring the constant out front, and I can do a trigonometric substitution. So I make my triangle, and there's theta, and my biggest side this side time is going to be a, so I'm going to put my x here and the square root down here. So you get x over a is equal to the sine of theta. So x equals a sine of theta. Dx equals a cosine of theta d theta. And then the square root of a squared minus x squared divided by a is going to be the cosine of theta. So this is a cosine of theta. So if I bring this 4b over a out front, I forgot my dx right there. The width of the rectangle is dx. So what are you going to put for the square root of a squared minus x squared? A cosine of theta. And dx is a cosine of theta d theta. So we have a squared. So if I multiply, take the a squared out, I get 4ab times the antiderivative of cosine squared of theta d theta. And I have to also change 0 and a. So if I look down to here, theta is the inverse sine of x over a. So if I put in 0 into here, what's theta going to be? The angle whose sine is 0. So that's 0. And then if I put in a, I get the angle whose sine is 1. So I'm at pi over 2. So now I've changed the limits of the integration. Now, if you remember back to the last talk, cosine squared we can't do, but we can make it 1 plus the cosine of 2 theta all over 2. So I could bring that out front, and then I can take my antiderivative. The antiderivative of 1 is theta, and this is the sine of 2 theta over 2. And we're going from 0 to pi over 2. So 2ab, and what do you get? You get pi over 2 plus the sine of pi, which is 0. And then when you put in 0, you get 0. So altogether, you get pi over 2 times 2ab, or pi times a times b. So that was quite a bit of work, but it did derive the area for an ellipse. And one other thing you could do is if you made A and B the same thing and called it R, then what would you have if A and B were both R? You'd have x squared over r squared plus y squared over r squared equals 1, or x squared plus y squared equals r squared. Then we'd be looking at a circle with a radius r. And what would the area be? Pi times r times r. So you could even show what the area of a circle is that way. So anyway, this shows one example where you actually have to change limits, and it shows you how you could find, using a trig substitution, the area of an ellipse, which you always wanted to know. So, thank you.